high density one like 256 would be still about a centimeter apart and usually more than that. So, this EEG, MEG have a high temporal resolution, low spatial resolution. On the other end, things like microelectrode array, MUA, single unit recording, multi-unit recording, these are really high spatial resolution because you can sort of precisely pinpoint where that neural event is, and the spatial resolution is in that sense great because you are going down to single neuron, but of course you are just picking up a needle in a haystack, right, tiny little area of the brain, single neuron, 1 or 2 neurons, that is it. So, and single unit means microelectrode is placed, it records from one individual neuron at a time. Multi-unit means a single neuron can pick up multiple neurons, unit is a neuron. Local field potential, as I said, was a sort of filtered version of that. Now, that taking it further, there are some electrical imaging, impedance type or imaging, and multimodal neuroimaging. More or less, though, what you can see is these are all electrical approaches, non-invasive and invasive. So, we have talked a lot about it. From the very beginning, I told you that this neurotechnology course lacks much in way of imaging. We are just running out of time. So, I did not cover it, but here it is worth talking about. So, for most people, the most familiar is fMRI, functional MRI. It gives us functional information, but it is really slow, right, because you have to apply the field, there are certain gradients and they create a bit of scan, but the other delay comes from the delay that comes from electrical function, whether it is from stimulus or spontaneous thinking, leads to metabolism, oxygenation change, and when that happens, blood flow increases. So, blood flow and oxygenation increase, but there is a lag, there is a delay of 1 to 2 seconds. An MRI itself to capture the image may take several minutes to capture the whole image. So, it is pretty slow technique. It does have a decent resolution, not spectacular today, down to few millimeter cube. It really depends on how intense the magnetic field. So, humans can take about 3 Tesla. There are machines that are 7 Tesla and more, but there is a bit of safety consideration. So, resolution is about few millimeter cube, which is still not bad. Then the PET, what is PET? So, positron emission tomography, and that is using radioactive tracers and labels, you look at essentially really metabolism. So, it is a bit more specific than MRI, because MRI itself is sort of magnetic gradient spin, so that what is called T1 and T2, you pick up the gray matter, white matter. Functional MRI superimposes on it oxygenation level. With PET, you get down to typically metabolism, you can even target some neurotransmitters as a way of tracking. They need to be really sensitive. Their resolution is quite bad. I mean, this graph is a bit older, MRI resolutions have improved because people make stronger and stronger magnet. PET resolution is not that great because you cannot produce too many detectors for detecting radioactive event. And SPECT is a cousin of that, single photon emission computed tomography, same idea. The in between is this FNIRS, functional near infrared spectroscopy. So, if the idea is that brain function can be looked at by oxygenation, then how about if we shine a light, just like we did with pulse oximeter? If we shine a light, it gets absorbed, we get a sense of oxygen. Why not shine a light in the brain and get a sense of oxygen? And then tomography, which means I shoot a light, record here, shoot a light, record here, and I could create a tomography like that. Now, the idea is good, but shooting an X-ray beam and picking up on the other side is good. With light, what happens? Well, not so much the reflection, but it's scattering. It scatters, it bounces off all the neurons and axons and so on, so get diffuses. It's like sometimes you have seen the glass that's transparent versus diffused glass, so the image looks blurred, right? If you look through it blocks sunlight, you can use sometimes diffused glass because it scatters the light. So FNIRS is is a valid tool because light laser can be shown quickly, the optical signal picks up very quickly. So, that way it looks quick, but in reality because it is still picking up oxygen. So, the change in oxygen at the location of brain activity, the change will also still occur slowly. So, it is slower. The resolution now it is up in the air. I think that it is low because of scattering. So, if I shine a light and I pick up here, there is a lot of scattering. So, you are not going to get very good resolution yet, but people are steadily improving the technology. Even in we talked about Neuralinks and such for doing BMI. That way there are people who have created at a startup and some research in FNIRS based BMI, and there are research papers and all of that, because I think I do motor imagery, oxygenation changes, therefore I can operate the BMI. There are some very subtle versions of this which are not so slow, both for MRI and for optical, but these are very, very exploratory. So, there is some kind of something called early signal in MRI that happens rather quickly, and its source might be not related to oxygen, but something else. And so, near infra also there are some claims, but they are not very, very well validated. So, this kind of gives you that this is cognitive work is going to be done by looking at the brain as a whole. That is the whole point, right? That if we use lots of electrodes, EEG, MEG, or PET and MRI, most likely really the dominant tools are EEG, if you can afford in some center MEG, and then FNIRS and fMRI as other alternatives. Okay? So, that is
Sir, on time basis, what temporal means?
That is time. How so what is the time before which we can get information? And so, in neural signal the time is every spike is information. So, within a millisecond or two, couple of milliseconds you have information. Now, one spike alone may not be enough. So, you might have to still capture 100 or 200 spikes before you can make some decision. In that case, it might be a couple of 100 milliseconds. But if you had the ability, remember in the tactile I said the first spike might give us information. So, in that case it would be at a millisecond resolution. In fact, our spatial thing we are getting down to microseconds. So, the time there is that with an FNIRS and fMRI, the time both ways, how long it takes to capture the signal. So, with MRI between gradients and construct the image, scan by layer by layer and all that takes a bit of some time, but also the change in oxygenation with activity takes time. So, by the time I move my arm, therefore, my motor cortex works harder, therefore, blood flow increases and oxygenation changes, it takes time. So, it is slower. Okay. So, you have seen this video. So, EEG of course gives us a very high resolution, and because of that high resolution we are in theory at least able to decode some information like movement of hand and fingers and so on. It is very difficult, it is just a early stage demonstration, but EEG carries very high temporal information. So, how do you get more or get a lot out of EEG? Well, you get it by you can do high resolution EEG. I mean, most of the time in the lab you are doing 0.5 to 100 hertz, but there are higher frequency carrying like gamma and high gamma. I think you go beyond high gamma 150 hertz or so, there isn't much information. The signal power is too low, and I had shown you a spectrum for that, and you knew. So, the gamma band power is very low, and so you can sample at 250 hertz to few kilohertz. The EEG it says 32 to 255 and 12. Frankly, most people will get by with about 32 to 64, and you get pretty good information to produce networks and connectivity and so on. Those who want to do source localization, they need to construct the field. So, from outside sample try to predict what is inside, and the more you have the better. So, if you have the full image of the brain and those 256 electrode telling you little bit everything, it is easier, it is better mathematically to construct the source of activity like seizure focus. But it is expensive, hugely troubling, might take 1 or 2 hours to put up electrodes. And for people who are doing practical or you want to do cognitive in a awake behaving acting state, like real driving. Well, then I just need to wear a head cap that's with dry electrode and kind of very elastic, something that applies, put it on quickly, like you saw in that Nissan video. In that case, 2 to 8 channel, but then it's what you get. In 2 channel, you're picking up just a little bit of window of this or that. I mean, you're not picking up what visual cortex is talking about. The third bullet is rather interesting. We all think of EEG and brain activity as somehow reflecting of our mental processes, right? So this has to do with, like, I'm doing something, I'm typing, I'm dancing, I'm calculating. But what has over the last 5-10 years become really hot is what's called resting state brain activity, meaning even at rest we are incredibly active. So some of you, now that after lunch, are incredibly active digesting your food and thinking about this, or others are thinking about the test, and some of your mind is very active, you are thinking. So resting state MRI has started to provide new insight into the brain function. It might sort of like, maybe we could think of it as daydreaming. So it's maybe you are resting, but maybe you're not. Those of you are studying meditation or something, you could get a lot of scientific insight into more westernized popular science version, because meditation is studied mostly in Asia. Some new researchers, believers in West like to know more about meditation and apply good rigorous tools. But resting state, everybody is caught on in a scientific way, as if like that's a kind of window into our thinking, mental state. And just the intriguing part, that brain is actually never resting. So if somebody tells you after studying, oh, you must be tired, go rest, the brain is not going to rest. It just attending to this versus that. So just because I'm doing a lot of mathematics homework doesn't mean I'm any more tired. It's just I employed certain neurons, right? And so resting state has caught a lot of interest as complexity, because just you can see the brain is a big complicated network. So don't think of it as a EEG at this site as a this waveform. So complexity, which is like how does a large system work together, right? As individual, you are who you are, but as soon as you all start interacting, speaking different languages, different culture, different interests, complexity goes up. And so how do you make sense of a complicated system? So these are kind of emerging areas, and because EEG is quote instantaneous, a little quicker, easier to work with, it has very wide use in these kind of fields. By the way, of course, EEG hand in hand is evoked potential, ERP and P300. They are also tools of the cognitive scientists and psychologists and such. And I told you already about functional MRI, the resolution and space and time. But you can see, you can produce wonderful little picture. They look like bright little dots where something is happening. There are people who question these bright dots mean anything. Yes?
Sir, how is resting state related to fatigue, workload and attention?
Not in the context of scientific research. I think they are very different. I mean, in terms of semantics, like behavior, of course, there is a continuum between resting to working hard to mentally challenged and then fatigued and stressed and all that. But when we use the word resting state in the scientific sense, it means you are essentially not functionally doing a task, and you still find the brain is active doing something. And obviously that motor imagery while doing nothing might be a phenomenon of resting state.
Sir, can at resting state a person be fatigued or have high workload?
You can do research on it, write a paper and tell me. I mean, those are the interesting questions coming up, because you see how new old things suddenly become new because people have a new perspective. So you may be working on mental fatigue, kind of relatively old problem, everybody is interested in. Pilot is tired, what can you do? Resting state is intriguing because it's new, the brain is not really resting, let's find out what it's up to. Now you say, you're mentally fatigued in the sense you've been challenged with lots of calculus or neuroscience lectures for 1 week. Your brain is very, very stressed and tired or whatever, and now say, okay, that's it, I'm going to close my eyes and so-called rest. but you're probably not resting. Maybe you're recycling your knowledge, you're thinking about, did I learn anything, did I waste my time, so brain is active. And so it may be different than pure resting. I wake up in the morning, take a whole day holiday, do yoga, meditate, and then you take my EEG in the evening. That's really perhaps significantly different resting. So resting state is not one state, but all it is that you're not doing functional activity. Okay. So now you need tools, right, for these kind of brain models and analysis. So this modeling, that means signal processing I've touched, right, that you can do spectral and wavelets and entropy and autoregressive modeling, and a lot of signal analysis tools are employed. Well, when you have lots of signals, how do you analyze lots of signals together? So the picture on the left kind of is a kind of an attempt to do like an MRI like image of the skull or brain. So bright spot means that there is a high electrical field. So this is the kind of thing where either through mapping, there are two approaches. Mapping means that at every instant, the electrodes might be scattered, say 64 electrodes, or this is like a symbolically the head, because when you do EEG, you don't have the picture of the brain like precisely that you have with MRI. So you just pretend that it's a circle and you know where all the electrodes are, and then you apply a color to any particular frequency, or color to the power, or color to the power and frequency, in some way you make an image out of it, because by making an image it's a little easy to understand than those 64 channel waveforms. They were very difficult to understand, but if I create a graphical map by giving each dot power related value and then interpolate to fill up a nice beautiful color, it kind of shows me stuff is happening here, let's say visual cortex. And so that's called brain activity mapping or brain electrical activity mapping, because you're creating a topographical graphical map, and it's easier to visualize. If it's, again, you could with naked eye pick up a seizure focus or so, but it's not that easy. You could pick up some motor or sensory response, but again not so easy. It's not that specific, but it's a way to map it. Although beyond that you could also go into source localization, which is in some way more accurate, because you're going down to the source in 3D. So it's not the brain is just like a surface graph, it is depth also, right? So somehow you get the depth, and that's by treating brain as a conductor, and you can assign that if there is a voltage here, this is the conductivity, what should be the voltage here. So if I make 1, 2, 3 point measurement, but vectorially I can project down and say, okay, voltage should be here. If that voltage is very high, you can say maybe that's what the seizure focus is. So brain electrical imaging is like that. It's more or less by interpolation. It's not like a true image. And now you can, when I say univariate, so you can just simply look at some frequency, but then you can also look at multivariate. So bivariate and multivariate, which means don't treat brain source as if like there's a source. There's always one thing is talking to another. I'm moving my arm, so sensory and motor cortex are connecting to each other. But in a multivariate, I'm moving my arm, I'm seeing the object and touching and feeling. So frontal lobe is planning, occipital lobe is seeing where I'm going, motor cortex is planning and reaching, and sensory providing the feedback. So it's kind of like a complex multivariate picture. Everything is sort of connected to each other.
Sir, at the bottom image, is it any relation to diffusion tensor imaging?
No. So what the question, I'm not covering the topic like DT MRI. Diffusion tensor MRI is a MRI based technique. So they realized that, see, MRI is essentially tracking water molecules, and so it's the spin is changed by the water molecules. In diffusion tensor MRI, there is a realization that if you have an axonal track, the water is more or less likely to go along the track. So what if you do the imaging anisotropically, meaning allow and separate each direction? Then if it's an axonal track, your signal will be stronger in that direction and not as strong in other direction. And that's a diffusion tensor MRI. It's very useful, powerful. It almost constructs what looks like axonal tract. Now again, exons are few micron and all of that. So diffusion tensor cannot reproduce truly axonal fiber, but it creates a fiber bundle like sense. So it looks very white matter detail. Both MRI and diffusion tensor, the images look great, but there's a lot of statistics and data presentation involved. And there are people who are kind of skeptical about what they mean. In fact, there have been papers completely challenging that MRI is anything at all, a functional MRI. But by and large, people go with it because that the bright color that you should see is some kind of statistical test to show that bold, that oxygen related dependent signal is sufficiently different and changed, and that's color coded. But you know, our human tendency to look at a picture like this and believe it rather quickly, and so it's become very much a gold standard for cognitive science work. And those who are doing, so you can do univariate or bivariate or multivariate analysis with EEG, or you can do it with fMRI. Is this colorful dot have anything to do with each other? But you know, that kind of causal, directional, all that. With EEG, MEG, there being speed, you can likely do that better. With MRI, when the speed isn't there, to build the network is not, you can't really build such good temporal network, but you can do spatial network. So these are all very powerful techniques. And as I've been talking to some of you, you're all sort of dealing with minimally the nuisance things like artifact removal for EEG, like it's eye blink. With MEG, you know, gradients and any movement and heartbeat pulsations, and all any movement will do it. When you do try to, a very obvious thing that should occur to you is that, oh, why don't I combine EEG and fMRI so that I can get temporal resolution of the EEG and spatial resolution of the MRI. You know, it could be a little bit here, so it's better resolved than it seems. So I think people are interested in something, but it's very difficult. EEG electrodes cause artifact, MRI gradient cause artifact in EEG, so it's very challenging. Those equipment are quite expensive. Otherwise, you can go into EEG, and natural thing is frequency analysis, but you know, the frequency, if you look at EEG, it's not like a single frequency, it's getting modulated. So there are more advanced tools like coupling, what's something called bispectrum, which is then has been used successfully for depth of anesthesia. Phase, you know, remember we do Fourier transform or something, there's both amplitude and phase. Phase is a little harder to interpret, so it isn't used as much. And really more emerging and popular tool is graph theory, to really use sort of computer science type tools to look at what's connected to what, is it causal, is it directed. You know about gamma, all of that. But again, going in the direction of this network theory, you know, you need this state. So the causality, right, is the, did I see something and it caused me to move the arm? Then in that case, my visual cortex signal should precede my motor cortex, right? So there should be causality, right, which means this leads to that. A correlation doesn't show cause, it just shows this is correlated, but it's not temporal activity. So Granger was actually a business finance type professor at Caltech. He developed this kind of theory for economics and finance, and it has then be very heavily adopted in signal processing and imaging and so on to look at causality. It makes for an interesting tool. Spectral version of it is coherence, are the two signals. So it is auto spectrum over cross spectrum. So if any given signal X has a spectrum, any signal Y has a spectrum, and there is a cross spectrum. So auto spectrum X, auto spectrum Y divided by cross spectrum is a coherence. And then partial directed coherence, it's a way to get the direction out of coherence, because coherence of X, Y over X, Y is not directional. So how do you get directionality of frequency? That it's essentially like frequency waves are traveling in the brain, you know, then it's partial directed coherence. Directed transfer function, right? All the engineers are used to the idea input, transfer function, output. Add additional directed function. I'm leaving out all the equations, but that's, and then of course there are other modification, multiple this and that, multiple input, multiple output, but that way think of brain as a box and this bunch of input came and output, and we have a wonderful transfer function with direction, right? Engineers will fill. So that's why I said this is cognitive engineering. You know, we are applying what we know in engineering: causal, connection, coherence, directed transfer function to study brain. Cognitive science would look at lots of brain images and said something is happening there, and a behavioral psychology person would say, okay, well, you're behaving oddly, you are not looking straight at me, or you are falling sleepy or whatever, and by the way, therefore brain activity changes. So they look at behavior, and all this mathematics is a problem for them. So this is how we can divide up our work. So you know, when people are making these kind of networks, wow, looks good, right? Things are happening from back to here, and arrows are pointing, and bright arrow to this, and it's very live and dynamic, right? Very brain network. This is a highly, you know, this is some kind of a task, but you can see that there's lots of stuff happening out here. You know, maybe a subject is given a task to look at an object and do some manipulation or calculation. So most likely something like that, right? It might be tied to doing calculation work. So visual cortex and all that is very active, and frontal lobe is very active. Not much in the motor sensory area in the middle, and not much happening on the side on the speech area. You can see the resolution is pretty low. It's little dots are where the electrodes are. And now these arrows are being pointed, and that arrow is essentially the color and is the strength of either coherence or directed function or whatever that you're using. So sort of, do you all get, look, I think I'm already seeing a lot of droopy, sleepy eyes. I should have done this in the morning and neuromorphic later, but it's a little heavy stuff, and this is all without math. So I don't want to make it too boring. So it might be a good idea. This is the way I can pause and catch attention. Anyone has a question? Do you understand what I'm talking about? Yeah? Sort of, okay, good. See that blood flow has gone to a little different part of the body. So there's a little bit of oxygen deficiency, and can't keep up with this directed transfer function and all of that. It's a little challenging, you know. So I understand that, and
So you should have the charger.
oh yes, the same. Okay. Oh, the chocolates are there, but I've not been asking difficult questions. Oh my God, so many chocolates are left. Sorry?
You can feel the happiness.
All right, go for it.
So he won't distribute. No,
Go ahead.
Sir, you didn't say about anything, single unit recording. What is that?
Oh, I did say. That was when you were in a little theta wave activity. No, single unit activity is the single microelectrode recording. In a microelectrode, if you very carefully place it.
So what's ESI?
Let me just finish. Single unit meaning when you place a microelectrode at a neuron, and just very conveniently the electrode is exactly in the right place where it produces action potential from a single neuron. Reality is in the brain, the neurons are so densely packed that you're never down to a single neuron. You're always recording from multiple neurons. So that's called multi-unit activity. But essentially, it's microelectrode spike recording. Okay?
And sir, in this connectivity estimation, I will ask you before also that volume conduction is a problem. Since because of that, it pretends internally they are connected. But how to avoid that crosstalk?
Well, okay, so let me explain to all of you like the volume conductor. So in so electromagnetic field theory, you have a, see most of the time what you are used to is voltage with a wire going to a resistor and current flows. But if I apply voltage to my skin, it's going into the volume of my skin, right? There is no wire, its current is not, current is distributed, spreading around. So you have to treat body, brain as a volume. So that's why it's called volume conductor. And that volume conductor, gray matter, white matter, may have, all of them may have different conductivities. So when we do this sort of volume conductor activity, it means the currents is distributed in 3-dimensional, and more or less what we can separate is scalp, skull, CSF, gray matter, white matter, right. So that's the kind of, I would call, volume conductor. You can do a little bit better by looking at directionality. So again, if you have volume conductor with DT-MRI, your model will be more precise, because your conductivity is now anisotropic. You are separating conductor in different directions rather than blurring it.
Sir, what is that DT-MRI?
Diffusion tensor MRI. Just now a few minutes ago I described that diffusion tensor, which is like the magnetic gradient field, the spin of the water is directional. So it's directional along the axon. So that way volume diffusion tensor MRI can give you even better model. So that is these are the technique. ESI, I don't remember the exact acronym, but essentially it's tied to electrical impedance. I don't remember what S is. So you can also changes in electrical impedance in the brain due to activity. It's very underused, so I don't remember exactly, but what ESI stands for, but it's sort of electrical impedance tomography, EIT and all of that. I don't know why they call it ESI. So people have used electric, but it's very rarely used. So the idea was, can I measure the changes in electrical resistance and create an image of the brain? But it doesn't work, because electrical current mostly flows through the skin. It never really goes into the brain, and so not a good technique. It doesn't.
So it's at the scalp level.
It doesn't work. So you keep coming back, but it's the least used. Doesn't. No, its intention was that just like light, when I shine a light, I hope the light will go from my head to come out, but what is the probability? Very few photons can come out. Similarly, if I apply electric current between here and here, the current will go, but current, you may think that if I apply electrode here to here, the current will go, but it's really will find a path of least resistance into the skin. So most of the current stays on the skin, and little bit goes deeper, and then internal distribution, and it's got the same volume conductor problem. How does the current distribute? Where does it go? What is the impedance? So reconstructing became very approximate. Now, if I mean, it probably can separate CSF from, or ventricles of the brain from other areas, gray matter, white matter, but resolution and then change in. So it's a kind of technique used for cerebral edema, right, like brain fluid flow. Did the chocolate get finished? It didn't seem to come further up. This guy is sitting there. Oh, it's done. Sorry guys. Uh-oh, somebody cheated. I gave away too many rewards. Actually, I do have another bag for tomorrow. I was going to take it for some nephew or somebody. What the hell? You guys are all going to be my nieces and nephews. Yeah. All right. So we wait till tomorrow. Okay. So. Huh? Oh. Well, this is probably, read carefully, it's probably from Belgium or somewhere. So
order it on Amazon.
Yeah, so we'll go for chocolate to Belgium and do sort of.
Imagine it's some kind of EEG, right?
Exactly, link it to EEG. Effect of eating chocolate on EEG, happiness. See, happiness research, all of that. Very good. Okay, so I mean, these are very good tool to compile imaging with functionality to get that sort of dynamic events. So now, how you could create it. So look at like all the EEG electrodes. So you do create these vectorial connection. Again, without a lot of it is without mathematics here, so that you can get an idea that whether you signal and do cross correlation, which is in time. You can do coherence, which is in frequency, partial coherence, which is if you have two sources, you apply coherence to source A and B, and is it connected to that. Basically, you are drawing graphs to connect this to that. So, there are a lot of graph concept. You can see that it can be applicable in many fields, in social sciences, in economics. If US raises interest rates, what happens to cost in India, because India has to raise interest rates, all the money goes from India to US. So, is it causal, directional? So, finance people. So, these are really standard mathematical data analytical tools. So, we just apply to these networks of EEG or MRI signals and create these kind of networks. Now, if you have a more detailed brain image, then you can of course place the electrode better directly on the brain and it looks better. If you do not have it, like one of you went to some hospital and collect data from patients who are meditating, but you never took the MRI scan of the patient or CT scan. So, you did not have a picture of that each patient's head. So, now you draw this circle and put them approximately, hope that there is a good localization. So, this is better, this is definitely a big approximation, but for many studies you can't do CT-MR scan and get more accuracy. And really better would be, I mean, this is the courses, this is better because you know that this patient's brain looks like this, but you are still placing an electrode because the brain is inside. So, you are placing electrode. So, at least you can tell better this frontal lobe and this and that. Even better would be source localization, so that it would go into the brain and align it and assign it to particular deeper regions of the brain it is appropriate, but this kind of works well. So, this is a place, this is a technique called shortest path length. It is another way to look at it is that if the signal from A to B has the highest short correlation or shorter distance, that must be the strongest. So, why not take a look at that? Remember, it ties in with our thinking that a lot of computation in the brain occurs local. You guys sit and talk to your neighbor, a lot of activities are local, very fewer, and even brain fibers are local. They do travel, but I think there is a very hyper exponential curve of number of axon or number of neurites or dendrites with distance is almost hyperbolic. So, most of them are very local. That is why the idea of cortical column, and very few and very few that connect long distance. So, the path length is something similar, that signal over a short distance. It is a mathematical formulation, but let us say that we put somebody to a kind of increasingly demanding task. So, we do that, then this metric seems to track the level of demanding effort, and in the meantime you see the brain activity. So, you see the reductionism is like this, that you get the, I could have shown you 64 channels of EEG waveform, or I can show you these networks, or I can blur it and color code it and make it look like this. So, that makes you look like something really kind of MRI sense, makes it look bright, or you can say I have no idea what is going on. So, give me a single measure of how much are things local versus global, and you can see that there is a
Global in this scenario.
well, I mean, it is a frozen picture, but you can make up your mind, see how it goes, see very local and then spreading everywhere and getting more and more complex, and towards the end something gets heterogeneous. So, it is this measure, whatever it is, came out with, it tracks the amount of mental workload, very empirical, but it is a measure that somebody can use, right. I mean, who is going to use that? It's a lot of information there. I mean, you have to sort it out, and if you gave you 64 channel information, you got a lot of information, but you do at least get an idea that it's instantaneous, it's very quick, it's happening. It gives a virtual sense, but you take the EEG segment a few hundred milliseconds, do the Fourier transform or correlation or coherence or create the path length and all of that, and then sum it up for all the different paths and different things developed until you get this single trace. But if I had one of our speakers, he's working with Defense Department and he's trying to track the pilots, they're not going to sit for all this stuff, and some boss comes and says, well, show me my pilot, is it concentrating or not? Well, you show the plot, and here is you're flying and everything looks good, and now the mental workload went up, and a top pilot would look kind of like this, nice and cool, and stressed out one look like that. Okay, she is a pilot, he's gone, that sort of thing. So, I think it's a simplification with all its problems, but it makes it possible to follow mental workload, mental tasks. So, sorry, I thought I won't give you a question. There are. So, these Granger, these are kind of like these equations, if you can see. So, these are Granger causality in a spectral domain. This is a bivariate model. You are all getting slides, so you have these, so don't bother to hurry up and write down. But I mean, it's signal 1, signal 2, they are autoregressive parameter model, and of course some delay j. So, j equal to 1 to p, it goes here. So, signal x is x1 is model as a time series, x2 as a model is time series, and then you find the interaction between the two. But if you do it in Fourier transform, in a sense, this is a cross transform versus auto transform. So, Granger causality is not necessarily reciprocal, meaning x may lead to y and y can lead to x. There is no directionality. That is why there are these directional functions sometimes used.
Sir, is there any intuition to go for bivariate?
Well, I mean, the intuition is to keep it simple as far as possible, unless you have a really strong reason to believe that multiple sources are acting to interact with each other, right, and multivariate. So, it is easy to, well, I mean, it is natural, it is very likely that things are much more complex than you imagine. But again, let me go back to the very simplest thing about sleep or something. Of course, even in the gamma band is affected, surely, but the gamma band power is so low. Why, when you can detect sleep staging from beta to alpha shift, you are done, right. So, keep it simple. So, that will be done by spectrum. Now, in depth of anesthesia, first decade or two when I was grad student, around that time, everybody was using spectral analysis and brain map, those beautiful graphical map for looking at anesthesia, but never caught on until this company and the researchers who came up with this something called bispectrum. It is a higher order spectrum, it looks at correlation in frequency domain. And then they did a very thorough study of patients where anesthesiologists, 2 or 3 of them say, yep, you are deeply anesthetized or you are not, and they correlated that single number bispectral index from 0 to 1 to 1 means or 100% means you are awake and 0 means you are dead or something. And they found that at 60% all anesthesiologists agreed that you are sufficiently deeply anesthetized. They would have done the examination, eye pupil, pupillary reflex, pinch, pain, asking question, memory, anesthetized. So, they set a threshold of 60% as a suitable depth of anesthesia. Now, people buy their machine, sit there and monitor the EEG, and when it goes below 60% says, okay, we are done. I mean, they still do the examination just to be sure, but it seems to have survived. So, it is empirical, but it survived because somebody did a thorough job. So, now coming back here, any of these tools, if you go to bivariate or multivariate when univariate does not provide results. I mean, if those kind of crazy dynamic movies, if you have reason to believe that lots of interactions are occurring. So, this node is interacting, here, this node is heavily interacting. I mean, but then it's like this is sort of like a univariate going into different nodes, but if 2 nodes are very heavily interacting, you might go into a more complex modeling, because ignore all that stuff. What is the point in doing multivariate, every node connected to everyone coming at a measure, and you need to support by your intuition that task does demand frontal lobe, because you get a lot of artifact as well, eye blinks, you move and you will get some bright spots showing up. So, those can be artifact, but by using kind of common sense along with reducing the data, you can look at the connectivity better. So, multivariate model, it is the same. All of these, for again math people, it is like essentially you are creating a time series or a autoregressive models of this, and then you can have multiple signals, not single, and Fourier transform it, because then you can have it in a transform domain. So, spectral domain provides you a bit more analytical ability to algebraically do things. The time domain, a lot of those people who that kind of papers, you will see a lot of integrals and differentials, and in this is like Laplace transform or Fourier transform. So, it becomes more algebraic. So, it is a preferred tool. Directed transfer function is another causality influence between one channel to another channel at a frequency, and it is a transfer matrix. Then there is a normalized DTF and so on, and so on and so forth, right. So, there are lots of tools, coherence, auto spectrum versus cross spectrum of two different signals, partial directed coherence. So, you have two sources to feed into the signal. I mean, maybe just for simplicity, left eye and right eye feeds into the visual cortex. So, you want to be able to see whether how much is the input coming from left eye versus how much is coming from the right eye. Then if you just do coherence between eye to brain, that won't tell you. So, partial coherence may be, I am giving intuition, block the eye, measure that, block this eye, measure that. So, now you are separating partial contribution of each source into the output. So, that is a technique of partial coherence to separate when you really know that there are more than two sources. Quite often it is never simple, you need to have a hypothesis that why two sources are active. Maybe you are giving auditory input left, auditory input right, getting auditory evoked potential, you want to separate out. Again, I am giving intuition, it is easier. But when you go back to that kind of brain map, you do the partial coherence because you think that input here is coming or input there is coming from two sources, right. Maybe let us say here it seems to be coming from two sources, you have a logic there. I do not think I have a lot of logic, this is somewhere in the frontal area, I have no idea what is the difference between here and here. So, it will be a bit of an overkill. But if my experiment was designed that my visual or auditory input came from two paths, then I might apply these partial and directed coherence and those kind of technique to separate things out. Okay, so now you use this for this is in gamma band. So, signal powers the load, so noisiness will be high, but it makes for nice graphs, makes for nice research paper. You feel like you are trying to sort out this complexity of the brain, not that we really know like what this line means and so on, but gives an idea that at this time in the experiment there is a lot of this seems like a node or hub of the activity, that is it is on the left side and it is spreading elsewhere, right. Kind of started off maybe whatever this was, then it scattered all over, not much happened, all of a sudden it pretty much coalesced here, and now you might say during this particular task there is a left temporal frontal lobe is active. It is a kind of if you read that for language left temporal lobe is involved. If you were to derive that from EEG, you might have graphs like this and would pick up the EEG signals in this area and would shoot the arrows and network to tell you things are going from left temporal lobes to elsewhere. And so, that is how EEG, because it is non-invasive and a lot of other convenience, it is real time. You can, once you collect the data, you can go home, construct a right kind of maps and prune it till you reach some conclusion of where something is happening, and perhaps some like when, that maybe there was a time and after a rather problem was given, and after 1.5 seconds left temporal lobe activity tells you that this is what happened. So, this connectivity and network theory can help you temporally and spatially sort it out. Temporal resolution pretty good, spatial resolution pretty bad. Whether now when you look at these arrows, you have a common sense feeling that they mean something, or they are too noisy. So, maybe I do not want to give too much credence to what exactly that arrow with its color means. I can understand that everything is happening in left frontal, but I am not sure, right. The difference between this and MRI is in a sense not that great, but there is a tendency to associate, because the way the picture is presented and it is very static and like a bright dot, people are very readily veered towards MRI, that something is happening there. It is nice bright dot in this part of the brain, but MRI, when you go into it, it has its own statistical data analytical changes, and good scientists make a lot of effort to make sure that those statistics are well done. I mean, this is for some of you who are going to do this kind of research, EEG, MRI, all of that, functional MRI. That's the difference between, you know, top journals and not, that you do really thorough data analytics, statistics, because it's still in the end statistical decision. So I told you of like bispectrum and cross spectrum. So what does that mean? I mean, everyone understands that this is a wonderful, nice frequency, right? And of course, if there is some delay, then you can call it a phase. But all too often, signals are not clean. See, like what happens, this is a modulation, right? So the frequency from this to become slow to become fast. This one is seeming, waxing and waning many times. This one has gotten quite a bit more complicated, where both phase and frequency keep shifting from time to time. Or here the power shifted, the frequency remained. So what happens is that, and this is kind of looking a little bit more like EEG when you think about it, except also still the fundamental more or less is the same. It isn't spread across a lot more frequency. When you really get down to EEG, I mean, this might be, if you're lucky, some theta delta moving around, right? Very relatively pure. In reality, alpha, beta, theta are all mixed up and they're going up and down. So clearly, it is not single frequency, which we can separate by Fourier transform, but it's not stationary like static, where Fourier transform works. So you really have to take little short data and keep saying, oh, it's changing. And then when you go into it, oh no, there is a modulation. It isn't as if, because I can't run a Fourier transform, I do it, I see one frequency here, I'll see another, I'll see another. So it will be time varying Fourier transform. Yeah, it's something called short term Fourier transform, or you can see it as modulation. The frequency is getting modulated. Our radio frequency sounds are AM, amplitude modulation, kind of like this, and FM, frequency modulated. But then there can be more coupling. This is just one and one frequency coupling. What if there are several frequencies, alpha, theta, delta are all fluctuating up and down? I mean, brain is producing a lot of different oscillations altogether. There's a lot of research, people associate different things for different oscillations. Certain theta, delta, something, or certain waves that are memory waves. Sort of like if you throw a stone in a lake, a ripple goes, it feels like this point is connected to that through the waves. So lately people have started to assign value to those waves, that the reason why all these delta, theta, alpha waves exist are for what is called binding. Like it binds one part of the brain with another, right? If the wave is going here and here and here, you know that when it starts here, it's going to that. And if the wave is continuing, then this part of the brain and this part of the brain are linked to each other, even though they are far apart. So that's called binding. So which means there must be binding, right? So if I see your face and hear your voice, I recognize you. So I connected voice and speech into a fused result to say who you are. So this binding is another brain activity that helps you connect things that are happening simultaneously. But to be able to do that, you do need these kind of complex analytical techniques to be able to separate out these waves and give some meaning to them. So therefore, there is a sense that there is a coupling in the brain waves. In this kind of paper, in some analysis, they showed that there is more theta and alpha 2. They broke up alpha 1, alpha into alpha. Oh, it went. Okay, so they, in these people, they went back, you know, they saw theta and alpha 2. These are low alpha and high alpha. So this is there is certain higher coupling of these two frequencies here and higher coupling of these two frequencies here. So coupling is hypothesized to be the carrier mechanism for coordination of global and local neural processes, and hence supports the distribution of information processing in the brain. Right? Low frequency modulate activity or large spatial, right? Low waves, high frequency, so it's local. Low is wider. And so, and then if they interact with low waves and this and high waves come. So today's homework is go to the lake, throw some stones, see the waves going back and forth, stone here and see the wave goes. Now store 2 of them and see the ripples merge, and you know, and develop a theory of brain. Kind of like, you know, like how, what is that guy's name, Newton did that, like apple, oh, gravity, you know. So you get waves, brain waves. You know, you can discover something amazing by sitting at the lake here, you know. So that's the whole idea. So these are all theories of brain and mind. This is this guy is a very famous cognitive scientist. So whenever he says waves, everybody listens. So he is kind of like big proponent of these kind of wave theory. And it says that waves are, like I said, carry the information, provide the coupling. And you know, when they do sound experiments and evidence and statistics in a jargon, at some level very hard to prove, but in some level it's sort of understandable. And then you see the waves origin only in hippocampus, then you say yes, hippocampus does this or that. So graph theory is another very powerful tool. So what is that small world I showed earlier? So the connection here this is very regular this is called small world in the sense. So okay, so the way this plot is occurring, that what we did over a entire brain or something like that, let's draw it on a circle. So all those electrodes are nice in a circle, and this arrow are connecting what connects to what, right? So it's the same graph before, well, it's here, right? So you can see that something is connected to something. So this looks pretty regular because going from here to here, and this looks very random. Everything is connected all over the place. And so normal brain is something like this, but we can, by designing a good experiment, we can calm down the brain to focus on it. Don't move your hand and talk and think and everything at once. Calm down, think 5 times 5, even though there's a lot of fluctuations. Some subjects' results will be very difficult, but hopefully get them to focus.
So what is the difference between these two diagrams?
This and this?
No, this colorful and the
Oh, yeah, just shown it in color. I mean, you know, you can read what it is, right? I mean, it's right to show that there is a hierarchy or diversity. Mainly, actually, I wanted to bring the idea that what they sometimes find, that very high hubs form where a lot of things seem to originate. Again, let's go back to the movie, and you can see that there is a hub here and there is another hub here. They seem to be very active, see, very strong hub, and then there are spokes. Very intuitive, logical. You can put it in a mathematical terms of connectivity and small world and all that, but these are all mathematical tools. And a hub, you can see it, you can feel it.
There are three types of hubs, the 3 colors depicting nothing else.
No, I mean, these are different ways of plotting, but what here this graph says that in this case there is a high level of hub and there are different nodes, and this particular experiment, whatever it is, that completely, this is a schematic, it's not real data. So what it's saying is, for this particular brain, for this particular task at that time, it seems like there's a high level of hub. So it's a high hierarchy. This particular node must be sitting high on the task because it seems to be controlling everybody. See, I'm the hub, you guys are spoke, little guys, I'm the big guy talking, you're listening. So hub and spoke. So sometimes you get that situation. Other time, if you're not a controlled experiment, everything to everything. I don't know why they gave this color code, but whatever it is everything. Maybe in your sleep, in your resting, you might see more regularity. That flow of information is more regular. So these are just pure schematic way for us to look, that you can look at this network this way graphically, or you can look at it analytically. So draw this like this, and now you can tell by whatever. So path length, maybe this has the shortest path length, and this one has a medium path length, right? And this one is long path length, and we can call it that way. And so this is a mathematical metric of like what are the probabilities of paths. So people do these are many different mathematical tools for network analysis. It has been used for telephone networks, computer networks, internet networks, EEG networks, MRI network. Well, you can plot it like a small world in a circle. This is a very mathematically jargonish, scale free, fractal, those kind of approach. Hierarchical, this little node is connecting to this one, so this is the lowest never, but this is a hierarchical, but then and then this, and this is on the highest hierarchy. So you meticulously sit down, or you can write computer programs to see who is connected to what, or who is connected to how many places, and then you find these 2, 3 are connected to each other, these are connected to each other, and on goes, and this is the highest node. Modularity, I don't remember exactly, and then hub and spoke and so on, and etc. So, there are a lot of these network analysis tools that are used for brain organization. Yeah, individual network measurement corrects one or several aspects of local, shortest path length, triangle. See, there are different paths. If you knew, right? I mean, so these graphics are not necessarily coming from brain research. They can be from population networks, neighborhood, this neighborhood and that neighborhood, and people in this houses are talking to each other. Computer program, my network with this building and your network in this building, and there is some crossover point of the hub. So, it is a way to make sense out of this connectivity, and you give it direction and you give it causality, and how many this node seems like a hub node, because see, it is between 2 networks. So, it is like 2 neighborhood, and somewhere in the middle they all meet. Left part of the glass, right part of the glass, I am the where you all of meet, you talk to me, I talk to let you know. You do not talk to each other directly. So, these are tools of network theory, graph theory developed in many other disciplines, adopted by brain people, although sometimes brain people attract brainy people who come up with the theory that percolates elsewhere. Granger developed it for finance, smart mathematical person, and it has been picked up by a lot of other people.
Sir, talking about network theory, so basically in network, whenever there is divergence and so related to its node and its vertices. So suppose I want to disconnect one vertex from one node to another node. So the cost associated with that particular vertex can be added in a reverse pathway or in some another way. So if in some operation, if some part of the brain is damaged, suppose I am thinking that the brain is a complex network, and this particular network nodes are basically representing this particular task, for example speech. So we are doing experiment. So can we record or mimic that this particular region, speech region, is producing this type of information, and we are thinking that the brain has a distributed memory. So if we can train other part with that particular cost, so can it be possible that that particular man will be able in future to talk?
I think you are going too far outside my expertise, and also too wide spectrum. This is like I have told you, right, very common tendency of young people. I have been pointing it out. Suddenly you want to be able to start making grand theories. So you see, you need to have a name called, what is that name? Buzaki. If you have a name like that, you can do those grand theories. Otherwise you do something simpler. Grigori, his first name is Grigori Buzaki. Is a Hungarian guy, but he's a famous neuroscientist I think in New York somewhere. No, but my point here is that you can do all of these. You can do anything you want. Will people believe you? Can you validate it? Can you verify anything? You can build the theories. I mean, you can make any theory you want. I am the most important person. I mean, what does that mean? It's just a mathematical construct that somehow more arrows are coming here. But it might be the most important brilliant person is sitting there. It's other people are too stupid to talk to this person. It's what you make out of that. So you went into this kind of speech, and yes, I suppose you could draw those networks, but speech is so complex, right? I mean, think about neuron spike, action potential, millions of neurons, no clear organization. How do you convert that into frequency, tone, vowels, consonants, phonemes, language, which language into, and you have a network of 1, 2, 3, 4. I mean, what is that? It's a very, very extremely crude representation. That's why I always go back to microphone analogy. Put a microphone on the building and figure out what this lecture is. Can't do it. Too much noise, too much clutter. So point is that I understand this wish to explain and then explain traumatic injuries and so on. But yeah, it's possible that if there is a traumatic injury and then there is a gap, this network never activates anything like that. For normal people, there is always activation. Maybe you present some picture to the person and tell them what it is and describe and explain. So you would expect visual cortex to be active, you would expect frontal lobe to be active, and a bit of talking you would expect here and there a bit of side activity. And what happens is, whoops, never anything here, but always something here. And you know from prior work from lesions and tumor that temporal lobe left side is usually speech, left is more dominant. And you know, this never shows anything. It reinforces your notion that. But to say that there is some linguistic something happening, can't tell. It's too coarse. You know, again, why I've used Galileo analogies and so on. Your desire to want to know the world or the brain is much farther than the reality. So imagine yourself in Galileo area, sitting on the mountain, looking at the stars and moons. And you want to know, I mean, I can understand how does this universe, where did it come from? Is it expanding or contracting? You don't have the tools, you don't have the perspective. Galileo, you know, your perspective was so skewed that you thought that, you know, everything rotated around you, not even around the sun, or that there were nothing called moons, you know. So when you have such a distorted perspective, your deductions will be very wrong. So our perspective of the brain is very distorted. We have too few samples. That's why when I talk tomorrow or later today, I don't think we'll get there because it's taking too long. Human Brain Project or saying, yes, let's get to it. Let's not do very low undersampling of neurons, you know. Let's build a model for billions, trillions of neurons. Let's just do it. Or in US, they're throwing the challenge. They don't record from one neuron, a few single unit, multi-unit, record from million neurons. At least it's a start. It's not billions, but it's a millions, so that we can get detailed network information. They're going to be in big trouble. Very soon after that, the call will be analyze the data. How do you, I mean, you saw those spikes, how they look, right? And to make correlation between one spike train to another of the two is already tough. How are you going to make any sense out of million spike activity coming at you all at once? So then they will challenge the mathematician and computer scientists, build the mathematical tools for that. This is like saying million people in Kharagpur or Kolkata, how are they talking and interact? Build a model. So there are tools available, and that's how they keep internet networks going and so on, hub and spoke, data load sharing, probability of connection. So same tools are applicable here, but don't jump to the conclusion. It's only as good as how well you design your experiment and create a hypothesis. If you are studying traumatic brain injury, you have a reasonably good evidence that there is a MRI or CT scan shows a big problematic hole. You stick this person in EEG, never during speech, even if intended speech and networks form, you can start reasonably consolidating the idea that Broca-Wernicke is affected. You see? So I think use that sort of step by step rational approach for getting carried away with your intuition, having fun, do it by the lakeside, late night, drinking coffee, tea, beer, whatever it is you do here. And you know, and maybe speculate what are the theories, like could we go further? Maybe some awesome theory will emerge, right? Fractal or chaotic dynamics or some quantum something. Okay. So better understanding, these are analytical technique, right? If I present you like that, very hard. If I present it like this, I start seeing something adjacency, right? Something is next to each other. So you can see some concentrations, pockets forming. So you can see that some of these electrodes, that means regions of the brain are working together with each other. So these are large data analysis tools available to you. There are a whole lot of them. I mean, just picked a few of them. Obviously, this is multivariate because you have multiple this, multiple that, spectral, and you are plotting it some way. So this is the kind of bit of what I would call cognitive engineering. Like I said, you know, as kind of people with quantitative mind, engineering minds, take on the problems of cognitive science. I only showed, you know, in the next lecture I'll give some applications, but basically only showed some example like cognitive workload. You can apply to anything. You know, we had subjects do mental calculations. Of course, you randomize it and all of that. And as mental workload, so that there's no artifact and moving and talking, and that way you can do stratified mental workload, and then series of these tools either from literature, from one field to another, try to bring precision and order to this, and a lot of other researchers are doing it. The more thorough your theory, more thorough your experiments and statistical analysis, such work goes to better journals and people believe you more. So it's still what neuroscience call epiphenomena, somewhere epi, up on the surface, you're looking at phenomena. It's that again like taking a picture from maybe 1 kilometer above on Kharagpur, and today you'll see lots of little ants running around, trying to do something. Lots of people, suddenly the campus has gotten busier, right? Yes. Suddenly the networks are crazier, but there are probably some hubs. At 7:50 there'll be a big hub is going to form. There's some famous person is going to give famous lecture. So therefore there's a hub, and then there will be the hubs will break into it, and let's do network theory, and so on. Traffic, same thing, right? So that we can create a hub and spoke, or maybe that's the arrangement. Airlines are really worried about these things, right? They care. Should they create a hub like Mumbai, Delhi, Calcutta, and Chennai are the hubs, and spokes go out everywhere? Or should that be kind of fly from Mumbai to Jaipur, and from Jaipur to Calcutta, and there to Udaipur, and it's kind of like a random flying wherever it's needed? So airlines have generally gone to that hub model so that they can concentrate all their resources in that. But some places like in Europe, it's so dense that there are hubs, of course, Frankfurt and London and all that. But then there are, for smaller cities, country, there is no hub, right? If you're sitting in Belgium, maybe you are going to hub, but otherwise you have basically it's small path length networks to all kind of local regions. But very few flights are going to go long distance. See, just like neuroscience, connections remain local, few long ones. So or then through multisynaptic get there far enough. So from Antwerp to Frankfurt to Mumbai, but not Antwerp to Mumbai, right? So that is rare. Maybe they realize that Antwerp to Surat, because Antwerp is a hub of diamonds and Surat is a diamond making, maybe there is a need for a flight. So there is be a rare connection like this. From Singapore, plenty of flight to Mumbai and Delhi, and fewer some to Calcutta. But there is a flight 2 days a week to Ahmedabad. It's double the price, but there are enough business people probably going back and forth that it's worth it. So that's a different direction.
This length maximum among the two distances.
It's one way to look at it, because in the flight you think of distance. In the brain, what is the distance? Distance may not mean anything. So that L, the distance, can be a variety of different factors. It doesn't have to be physical, anatomical distance. It could be temporal distance, it could be some frequency distance, it could be some other metric. It's just that it's a for mathematicians they use distance in a very generic way, not in a millimeters way. Well, there are words then tensors and so on, vector, tensor, and then in deep learning that tensor flow is the algorithm. So these are ways, right? So information is a tensor flow, that is the deep learning algorithm. But in a way it's trying to say what's connected to what, how do you flow the information.
Can we take a break for 2 minutes?
I think we are doing really well. I got your attention. We keep going. I'm about to go into quantum cryptography, don't you? Yes, take a break. The way people think. Soldiers fight and Alzheimer's is treated. But are we in control of the ethical ramification? Because there are the World Government Summit in Dubai in February, Tesla and SpaceX executive Elon Musk said people would need to become cyborgs to be relevant in AI age. He said that a merger of biological intelligence and machine intelligence would be necessary to ensure we stay economically valuable. Soon after, he created Neuralink, an intention of connecting computers directly to human brain. Brain computer interfaces are not a new idea. Various forms of BCIs are already available. Can you guys read it, or should I read it aloud? And there's all this link, Moody's hand during the power of concentration. There's all the EEG placement. He wants to use BCI. So someday when you do that, remember I taught you bidirectional. and goal of cognitive enhancement. This is the guy. Remember I told you that he sold his name. Here's the one, that traumatic injury rat experiment I showed you. Brian Johnson is another billionaire. He is testing neural lace. So he founded a company called Kernel. You can always name Google, why not? Facebook CEO Zuckerberg said people won't be able to share full sensory and emotional experience. All that is happening in a building 8. Or it will be unlikely to be available anytime soon. And some more may be unrealistic. Again, Mohseni, so he's not the most famous person, but he's in the press. His name is a electrical engineering faculty, but he got into the limelight because he sold a name. He started to put up, copyright different names, and I guess they were looking for it. They liked the name, and so this guy Ted Berger has worked on memory, hippocampus. So hippocampus damage is, I'll record and stimulate from here to there. So by doing that, he's he's thinking that he can memory, and it's been very controversial. But he's been doing it for 15 years, very limited progress. Human Brain Project was, Henry Markram was that like $1 billion. It's fizzled out, but the program is there, but Markram is not the leader. So DARPA, Defense Agency, invests in these things in a big way because understanding the brain maybe for soldiers. In UK, Essex is BCI NE lab, neural engineering lab. Whichever goes in the press, lots of people are doing it, but some people are lucky to get in the press. Is that we need to better understand how human brain works before, and so there's a lot of investment in basic neuroscience research, the Brain Initiative. Whenever there is a talk of enhancing humans, moral questions remain. So that's, we have not covered here, ethics, morality. So neuroethicists are working to give advice to policymakers what should be regulated or not. So you see, brain game, the freaky factor of AI. Elon Musk say AI could lead to Third World War. Goes on and on. I think it's all interesting, but let's stay in the context of the course. I thought that one point here, this link might be interesting. Let's see. Moving the hand with the power of concentration. Paralyzed man moves arms using power of thought in the world first.
We've been able to take the electrical signals which represent his thoughts and use that to control stimulation of his arm and his hand.
We've bridged his spinal cord injury. He can now think about moving his arm, and his arm moves.
The participant also uses a mobile arm support to support his arm against gravity, but that mobile arm support is also under cortical control, meaning by thinking about it, he causes the mobile arm support to raise and lower his shoulder.
Well, it was amazing because I thought about moving my arm, and it did. I could move it in and out, up and down. I'm still wowed every time I do something amazing. I ate a pretzel. I drank water. It really got good. One day, they had some mashed potatoes. Lo and behold, I was able to eat the mashed potatoes really well.
It provides a demonstration of feasibility so that advances that are needed to make this more clinically acceptable can be made.
There is room for significant growth. We are at the forefront of really understanding how the brain functions, how to take advantage of our knowledge, and could see exponential growth.
I'm always wanting them to do more. Seeing the possibility is one of the biggest goals. Yes, I'm injured, but it's not like my life stopped when I got injured. It's going to help out a lot more people for years to come. Somebody has to do research. If nobody does research, things don't get done. Now we can tell the world it's possible to reconnect the brain and make the arm move again.
How's that? Good. Okay, so motivating.
Sir,
All right.
using ECG?
No, he's using that entire microelectrode implant system, two little bumpy things, microelectrode arrays in two different locations. He was moving in the sense that there is an XY control, maybe Z, I'm not sure, but rest of it is supported by this machine because he cannot lift arm, all the muscles are not working, so it's just giving a direction. Essentially same thing as moving the cursor left, right, up and down, but in this case to the arm. Like one difference, this group out of case one, so they electrically stimulate the muscle. So muscles can do something additional rather than just move. Okay, so there are all these various interesting options. Someone of you know how to download from this to a PowerPoint? Hmm? What is it? Sorry. Oh, there is an app. There's a website. Okay, maybe afterwards because right now it'll eat up time, so I can save it for future talk. Okay, keep vid. VID. Okay, all right. So hopefully it'll save it. Okay, so we're good. Cognitive engineering 2. It'll be very light. Little more videos. In fact, in the spirit of this, the one I showed you before. Not learn all those a lot of mathematics or network theory. But in a way, what can you do with it? So you know, there are different kind of applications like mental fatigue, mental workload, you know, some of these things you're interested in, EEG biomarkers for creative thinking. But a lot of it is right now today, most people are focused on this workload and fatigue and in a context of different types of applications. So let's take one example. This is a what is called psychomotor vigilance test, where you're given a lot of different problems or challenges, right? So for example, you know, you're supposed to add or something like that, and then you know you look at reaction time, because you want to be able to, if you know something and you're quickly done and understood, your reaction time is shorter. So reaction time is pretty well associated with mental capacity, mental workload, or alertness. So you know, when you consider something like an alertness, and reaction time is very good. We'll later show like eye artifact, eye movement is also very well related to that. So it's a PhD thesis of one of my students. She came from one of the IITs, I don't remember which one, and she's just defending next week. It's about vigilance and alertness, and so she used EEG and eye tracking plus reaction time together. So this is you can design a study. So in this kind of thing, it becomes really important to design these studies very carefully, because you know your data is only as good as these design. You have to randomize or you have to create a graded response so that you can separate, because you can see the heavy duty standard deviation bar. But once you look at this reaction time, you can see that it increases with different types of workloads, right? So if workload is increasing, so is the reaction time, you know, along certain number of subjects and so on. Of course, if you put EEG electrodes at the same time, then you can do connectivity analysis. And so now you remember this one I showed you, it's sort of for this. Well, you know, you can see the reaction time here and path length relates to that. So EEG, I told you earlier that we came up with this matrix that so this is that validation that I was talking about. If you guys go and collect the data and come up with this, so what does it mean? I mean, it seems intuitive. So at one level, yes, low mental workload with low level calculation to medium to high, and it fits. Okay, fine, but not a big surprise. At least I linked it up with reaction time. But maybe if you can link it with eye tracking, it's even better. If there was an fMRI to tell us where it happened, that would be better, because yes, EEG does localize, but it's very, you know, it's somewhat empirical, right? Because we fit all this electrode into a circle. So it's not truly, I cannot tell which region other than front or back or something like that. But now this technique is suitable for mental workload or mental fatigue, where over time your reaction time, in this case fatigue, your reaction time is reducing, and path length. So it might be a good test for a pilot or driver or a professor who has given 5 days of non-stop lecture, number 25 right now, I think. And reaction times, let me try my reaction. Oops. Okay. So that way you can look at mental workload and fatigue and so on. So you design good experiment, right? Like a math test, relaxation, math task, relaxation, block design, which is how statisticians do it. You must create in different blocks so that again there's no lot of bias, because you know if you just do it linearly, there could be bias to one to another. You get habituated, you understand, oh, next problem is going to be more difficult anyway, so let me get more alert, and you know, so that you kind of have to, very important main thing all I can say is that you should be careful about how you design things. And then of course there are all these, there's one of our postdoc has paper, symbolic transfer entropy. So entropy, I'd use the word randomic, and symbolic entropy means to random data you assign different symbols, right? It's kind of like saying letter Z is very rare, so high information, low entropy, letter E. So it's another technique, and you graph it, put it, and you say, yep, symbolic entropy is helpful. So more mathematical it gets. Small world techniques of mapping, these kind of a. So here then the conclusion was multi-frequency functional brain network based interfrequency coupling. The frontal brain areas oscillate on the dominant theta rhythm. So frontal brain areas shows a lot of theta rhythm, while parieto-occipital, so left to back, are more alpha 2, sort of higher alpha frequency. So it's an interesting observation. Since my name is not Buzaki, so I can't say what that oscillation means, but brain may have reason for this oscillation. I mean, alpha 2 is arbitrary, but clearly something from low to high frequency, the low frequency oscillation in the front and a somewhat higher frequency and oscillation in the side and back, it means something. At the moment we are just using it as a marker. So that's why some people call it biomarker. They are markers for workload or markers for fatigue. And if you make a tool and make it available, at one time we were approached by some company that monitors ships on a harbor, lots of harbor. It's kind of the same thing as like air traffic controller. So how do you monitor the air traffic and mental workload? If you make a mistake, you can have trouble. And when do you consider the air traffic controller is too tired? For a pilot flying Pacific Ocean, it might be the opposite, that they're bored to death until suddenly something happens and they may not be able to cope, particularly at landing or turbulence hits. So are they vigilant enough? So there's a sort of sense and hope that such techniques will be helpful. A lot of typical interest in defense, because they can use, heard the example that you could lose a plane because a person not desirably alert. So mental workload fatigue has traditionally been quite sponsored by defense and so on. The industry people tend to be more pragmatic. They need the answer, but they also need to be practical. They can't be making people wear EEG cap, and they're not interested in research studies. And then there are some counterintuitive issues. They've trained a pilot, some, let's say Air India, terrific pilot, trained for 10, 15 years. They don't want to know and prove that he is or she is very incapacitated or something. So sometimes they may not want to know as much, but nevertheless this technology is kind of interesting to people. So cognitive workload is in this case through cross frequency coupling. So you see there is different degrees in level 4 and level 5. So this kind of problem solving, different levels of workloads were given until you find, and based on the electrode, like I said, there were 2 networks that come about. Do I know all this, what these arrows mean? No, but do we get an intuition that stuff is happening here and stuff is happening? Yes. Do I have a biomarker? Yes, there is some sort of theta alpha 2 here and theta something here, and it's a nice technique or tools to monitor it. So now I showed that there's some similar work, and so external visual information stored in the modality specific region by the alpha 2 rhythm. and time lag between frontal and parieto-occipital sides in correct and wrong trial. So that's kind of interesting. So there's a sometimes you get a calculation right, it works one way. When you get calculation wrong, the network may behave very differently. Not so much a lie detector, but when you think about it, right, if you have an exam problem, if you know it very quickly. If you don't know it, you're pausing, you're confused, you're a little stress and complications, so brain probably can get to it. So in this kind of example, like theta power increased, alpha power decreased. There are others that have done work on single band or band ratio or classification. So that's why talking to some student, do your research. I mean, there's a lot of literature out there, and you really have to design your study carefully. And there's a lot of redundant and overlapping literature, and everybody develops, to publish your paper. You're an engineer, signal processing, come out with your own theory on your own technique. So how do you make it very popular and publicly available is always a challenge. So it's counter to one of the persons asking me about, well, we have all these ideas, we want to protect it. So if you're an entrepreneur who wants to make a product and distribute it, you probably do want to protect it. But if you are a scientist, you want to get famous, yes, you publish, but if you make your software or app open source, other people download it, they might use it, and then there will be more use and download, and they will cite your paper, and you'll be more popular rather than keep it abstract, opaque. So yeah, this is a very well known battery test. This is a very good way to get started to prove your algorithm. So NASA developed these tests where they on a screen they present a lot of information, like some industrial operator or even a pilot or somebody could be seeing on a screen, well, how much fuel is there, how much is brake fluid, how much is the engine RPM and exhaust, and a lot of information is there on the screen. So you have to continuously monitor to make sure everything is working at the peak level. So how do you actually monitor that everything is at the peak level, and how well are you performing at different grades of the test? So you can hook up a person wearing EEG. The nice thing about this MATB or MATB test is that they have structured it so that you can program, essentially input different types of loads. So how fast this is changing, how fast this is changing, how much this is, how often they are doing. So that way you could get some of these kind of, in this case, like equivalent of these 5 levels, 1, 2, 3, 4, 5. So you can construct this MATB into multi-level test. So you can see if your algorithm separates those 5 levels. If they can, then they can go into real world and apply and test this. So if you want to set about this kind of a project, then you'll probably certainly need EEG system. As I said, people buy, depending on how much money you have, people buy, the more the better, but the more analysis, more calculations. 16 generally suffice, not so bad. It's nice to have galvanic skin response as another indicator of workload or stress. EKG, EOG are mostly all of this for artifact reduction. So a lot of background work on signal processing and all that occurs. Otherwise, you do EEG processing, feature extraction, classification, all of that until you find your little metric, so that you can say what is the cognitive workload, low from high, and follow and track the person. All right, so let's play it. See all this, lots of things are happening. Sorry, it went too fast while you're recording EEG, and nice, wonderful, gradual, progressive performance from low workload to it's going up and going up even further. But basically, it's the same NASA battery test after first level to the second level to now it's being up to the third level. So green to yellow to red, if you let it go green, yellow, red. So it's a test setup to show that this particular algorithm is tracking different grades of workload and stress. So I think any of you is trying to develop your technique for workload or mental fatigue or all of that, maybe you should, because I think this is publicly available, so you can try it out, within your lab before you go to a patient or go and see a whatever meditation somewhere in Tibet or something. So then you can have a lot of these tools that I have described. So in this case, of course, there were this EEG. You can see there are a lot of artifacts. This person doesn't have seizure, healthy normal subject. So you really have to deal with, that's a really very serious problem. So this can be really problematic if you get these kind of artifact, power line noise and all that. You have to remove those. But now in this case, you see there is some with time, there is a theta band and alpha band shifts that are occurring with time in certain channels. So you can get sort of the pictorial view. Same thing is applicable in other things like flying. We set up a flight simulator. Again, it's not so expensive to get a Microsoft or whatever flight simulators on a screen is flight simulation. This is the whole EEG based system. Now to bring a bit more realism, we had the person wear the EEG cap and the virtual reality glasses or goggles, so that it's more immersive than this, and you hope that way it's more realism. Again, monitor a lot of EEG, look at the brain network and then stratify into different phases of demand. So in this case, as pilot is flying, that's what we'll see. So you see the workload is low, the plane is flying very smooth, all is well. Now the medium workload, the weather is getting a little bit bad. Yep, so the workload went up from green to orange. Now there is a bit of some stress is building up. And then at the phase 3, there is a lot of turbulence, flying demand. So yeah, you can see the plane is oscillating and he's trying to control and struggle to keep it going. Okay, so cognitive flying, so that way you can track mental workload, being this kind of mental calculation, flying, NASA battery test. So these are the ways you can assess stress, fatigue, whatnot. This is work into one of the PhD students. So she looked at things like surveillance, right? Suppose here is a complicated scene, and then there are people in there, except maybe somewhere somebody is a bad person or something maybe, and you're paying attention to normal situation and bad people. Now one change between top and bottom is like pseudo rain falling. So when rain falls, it adds your stress. Like imagine if you're driving, okay, you're going along and driving and driving and driving and driving. What's likely to happen? You're going to be a bit bored, right? But what if rain falls? Will you be will you be less alert or more alert? So yeah, so it's kind of counterintuitive, but of course you all get it quickly. Initially you'll be more alert until it keeps on raining, then your mental workload will be very high. You'll be alert, but you'll be struggling to also drive properly. So that kind of, it's a combination of mental load and such. So we flipped it around and said that if I'm giving this lecture, so you've seen me do this now and then. Lately a little bit I've gotten lazy, but now and then when I see and I'm giving a lecture and this and that, and then I kind of get up and see I'm kind of arousing you from your boredom, right? Because and I look at you have probably seen me look at most of you, so I keep you guys alert, because if I make eye contact, he's not sleeping, right? So I make, if they're asleep, that's different matter, but if you're annoyed, then I make a joke about this and that. So you can get bored and you can get right, but so this might be some teaching tricks to keep it alerted, but in general, how do you improve the arousal or improve the alertness of the person? Well, certain types of biomedical research, they're trying to do that by electrical stimulation or something. Of course, you can give tiny electric shock every time you fall asleep, give a little electric shock, but seems like that's not a socially acceptable idea. You can give a passive, there is something called transcranial DC stimulation, that's a passive, it's not very, you can buy it for a few dollars, or that means few hundred rupees. It's a simple battery based 5-volt stimulator on the head, and people claim that it improves alertness and whatnot. A lot of mixed results, lots of mixed research, low end, not convincing at a higher end. So one approach, like I said, I made you a bit more alert right now, just this, my sheer act. So you could make somebody alert. So here we said, okay, well, the surveillance is getting so boring, let's turn on the rain, artificial rain. So we call it cognitive enhancement with a bit of disclaimer. So here, see, lots of things are happening, you're looking at it, you're a surveillance person, boring, boring, boring. Rain comes up, oh, okay, what's going on? And now the bad guy came, I'm more alert to notice the bad guy who came in. So you're sitting there, the student is sitting with the EEG cap, there's the eye tracker, the computer screen for looking at the surveillance. So you're doing both eye tracking, from which we can do eye motion, saccade, and of course you can also add reaction time if you like. And so now, okay, here is surveillance, on the other side is EEG is happening, notice how some of the artifact and all that. So to do all this in real time, I mean, artifacts can be a problem, that's why you see all this kind of bumpy stuff that sometimes you just have to accept some of those noise. And then, okay, so let me pause. So what's going to happen is that this is that whole surveillance about 20-30 minutes, and on the y-axis is the I forgot what the indicator is, but some degree of measure of alertness. And so when you begin with very high level of alertness, right? So this is eye tracking saccade distribution, very high level of alertness, but after a while in a surveillance, the alertness is going down as indicated by eye tracking or saccade, right? So this is the monotonic period, and you'll see some decline. And then we are giving a challenging stimulus, challenging a person to arouse, right? So went down and down, rain, and suddenly there is an arousal, and then of course the rain ends, slowly again back to decline. Now you can't keep trying this again. I got up again and said, oh, come on, don't sit down, don't bother me, you ignore. So second or third or fourth time it's not going to work as well, but it is a kind of an approach to improve the arousal. You see, this is now by EEG measure. So in a sense, you could argue that EEG is not as specific. Yes, it does show decline, it does show arousal, and there are some bumps, but it's not as robust, at least in this subject in this one time compared to this. So the results are pretty good, statistically significant, publishable, but eye tracking is a secondary measure, even though it's kind of interesting, and it may well really have to do with the fact that it's straightforward, you're tracking eye. So measurement error, do you follow what I'm saying? It's not that eyes are better at showing my alertness or arousal, it's just that there's less error, versus EEG is so random and noisy that the tool to interpret that arousal are noisy. And so it is quite possible that results of EEG, it's not so much that EEG is a bad measure, it's just that our signal processing algorithm may not yet be good enough to capture the true changes, and a lot of things, right? So which location, which frequency, cross coupling, any of the tools. She is a grad student, like some of you are grad student. I mean, she has certain capabilities. She is not a mathematical EEG analysis person, so she used pretty straightforward beta alpha ratio as a way to assess. maybe something else might produce better results. So, so the idea here is that cognitive enhancement as defined by these kind of number of times that you can have a saccadic changes or certain EEG changes seems to improve, show that by giving surprise. So, people measure cognitive load and all that, that is fine. I mean that you are working, you have give more and more calculation, but what you really want is what Elon Musk wants is enhancement. Well, this is a trick way of creating enhancement. A trick way of teacher to create enhancement is certain, you know, do magic show, crack a joke, look at you in the eye, get up, challenge you with questions, right? Every so often to get your attention I ask you any questions. So, because I am talking, any question? Oh, what did he say? So you wake up, right? So now a little bit of arousal until you are back to dormancy. So you need to do the same because it is human. There is nothing you can do about it. So if you are here truly to learn, you need to find something to arouse yourself into that. Now it's a shared responsibility, right? I mean I am doing what I can, but I can't. If you don't engage, there is nothing I can do about it. So you must also fight your boredom, sleep by some tricks. You shuffle, get up, well no, get up, chop, put a hammer on the head, but certain things, take out your phone and play a little game. You know, your neighbor kicks you, but there is a need for that kind of alertness in our day-to-day certain workload. Just think about it, this 20-30 minutes of lecture, the ones who have to do hours of surveillance, the soldiers who are on the mountain looking for whatever terrorists and bad guys they have to work in this boredom, or the other extreme where they are flying or driving in a high stress. They are humans like you, although they are better humans in the sense they have conditioned themselves physically and mentally to do better. I have obviously conditioned myself better to speak for 6 days non-stop, but not so good as some Indian politicians. So you know, I promise. Is that possibility that I could try?
Yes. Sir.
Yes.
Sir, that PBT and the NASA battery testing. So with how you correlate those studies in psychological or psychological tests with the signals and all that. Means we conclude something from the EEG, then we have some scores from psychometric test. Then how we correlate with this?
Yeah. So I mean, it depends on how you frame your paper or results, right? If my audience is signal processing audience, that I have developed a new signal processing tool and technology, you know, then the bulk of my paper is going to be about the algorithm of how do I do theta alpha coupling and all those kind of things. And by the way, that for it gives me the gradation, and it's kind of validated by side. I don't do a lot of correlation. I just say that it's pretty obvious to the eye. I could do pseudo correlation as well and say p value of this or that. So that's the way I would approach that audience. But on the other end, if I'm going to a behavioral scientist, I sort of probably personally myself I would get into a bit trouble because they don't talk that way. For them EEG is like a black box, they couldn't care less, it's some EEG measure. For them the gold standard is the reaction time or something. And then correlation, they don't use the word correlation as loosely as we might use, because you know what is the data from one category to another category, they are different. So you know now you have to, that's why I said that all those behavioral and psychology people are very different. I mean their expectation of statistics is very different, and that's what my student and indirectly I found.
Sir, those test score maybe maybe subjective. One psychologist will give some score. And
that is another problem. So that is me as an engineer would exactly feel that. Psychologists themselves may not say that. For them it's a kind of gold standard, that's how it is. And yes, but very true that if they are the scorers, the test scores may not be consistent. Way back, you may or may not remember, but I said that for EEG, or epilepsy. Not neurologists don't agree. So if I'm developing a computer algorithm to detect epileptic seizure, how do I validate it if two neurologists cannot entirely agree? I mean the big huge case of grand mal they can, but other ones they may not be able to. So yes, that's why this behavioral research is challenging in its own right, because you know, this variability, observer versus the subject come in, subjects, if different trials, maybe something comes up, right? I mean, they may not have slept well the other day, they may have bored, we didn't give enough money, you know, there's a lot of, so we have done about 16, 17, there are 1 or 2 outliers, what do you do with that? So that's why I would say you really design your study very carefully. You really need to have a clear hypothesis. So in those theses one is the tools and matrix for cognitive load and assessment, the other one is this sort of cognitive enhancement, and third one, she and another student tried haptic feedback as a way, and actually the results are not yet publishable, because you know, if I'm driving and I'm feeling sleepy and a vibration comes on, maybe I'm aroused, but I'm also maybe distracted, so that we are sorting out, the data is not very clean.
Sir, then we have to consider both the, the signals point of view along with the psychological test.
It depends on what your goal is. Again, what I'm saying is that if you are a cognitive scientist, your goal is to figure out how brain works. Please go back to how I started. If you are a psychologist, you are talking right now like a psychologist or a behavioral person. Then your goal is, does this test help me figure out, I don't care whether you use EEG small world network or alpha theta ratio or something. What I want to know is arousal, alertness of the person, and is that correlate statistically significant, is this method reliable and robust, are there intra-observer variability, are there subject-to-subject variability, all of those things. If you are a cognitive scientist, you might say, yes, I am interested in that, but I am interested in when the workload goes down, which part of the brain is active, or if I want to do cognitive enhancement, which part of the brain shows change due to enhancement, right? I mean, you would be curious, right? So that when the cognitive workload went down, which part of the brain started to show that kind of a fatigue, right? And you would want to localize it. And more so, what is cognitive enhancement, that surprise or P300, or in this case that alertness change, that reactivity? Yes, it is observable to frequency, but you would want to know where and why that is happening. So that's what a cognitive scientist would do. If I am a cognitive engineering coming from that perspective, my goal is to use NASA battery test or this kind of test as a way to show that certain EEG measurement tools are a way to assess cognitive load and enhancement. So, you know, we come from different perspective, and so you as a student, scientist, budding scientist need to first of all assess who you are, what is your audience, where do you plan to publish, where do you expect to eventually find a job. And it's, of course, the most amazing work will not go to a top tier PNS or Science Nature with a breakthrough that something does that. Actually, there was actually a paper in Science, we were kind of like shocked how it got published, but it is about, they used a simple driving simulator, but they studied something like 30 plus young versus old subject, and I thought nothing surprising. They showed that older people have certain limitations, but it was very thoroughly structurally constructed, and I assume everybody gets to know that work because published there. But otherwise, you have to know your audience and publish in psychology and psychometrics kind of journal. They are not going to read equations, and they don't care about EEG. Or you're going to, our work is going to publish in Frontiers in Neuroscience, or Frontiers in Human Neuroscience, or Frontiers of Neuroengineering, depending on the bias and that. And if it goes to IEEE, Transaction of Neural and Rehabilitation Engineering, they're interested in algorithm. So you have to know your objective. If you want to commercialize it, you know, make a beautiful display, make the system easy to use. If it's a research tool, doesn't matter online, offline. If it's a clinical tool, make it very simple so that patient and physicians are not affected, right? So know your objectives, which is generally applicable to all of you. Like, why are you doing it? Who is your audience? You know, get to know that and accordingly maximize it. If you are startup people, you investor, you know, want to raise money, so sexy bells and whistle, you want to say millions of people will benefit, you know, saw that hype you saw in that Elon Musk video that I showed you, and you can hype it up that way. If you're scientists are conservative. Well, we have results, but they are statistical, but we have a lot of concern, and you know, we kind of cover it with a lot of caution, because scientists are careful and caution. They respect that, because unless you repeat my studies many times and so on. Okay, so it's something that you all have to learn to develop a good tool set, right? So now, as you saw, that you can discover something like, for example, there's a dominant region differences in those tests, in those work, the high vigilance, low vigilance, the difference when we took it, this shows up. There is a kind of low dominance and a high dominance area with not so surprising frontal. So, similarly, this is applicable in many things. One of the things we had implemented is 2-person communication. So, they are both wearing EEG cap and cooperating. The idea is it's like a pilot and co-pilot. If the pilot is not performing well, maybe should co-pilot at some point take over, or can they cooperate, or will they compete, and can the brain to brain, not that the brain to brain connection in this case, although people can dream of that as well, or other is that we would, to really get to know where it is and so on, we have to do EEG fMRI together. So that's another kind of thing. And sort of for military kind of thing is this idea like a cognitive helmet, right, that all of this worn into the helmet, so that helmet is constantly monitoring the brain of the soldier, so that this soldier is out there in the mountains, and this monitoring will tell whether the person is alert or not, otherwise all the terrorists will sneak in. So this would be like a futuristic helmet that has all these cognitive intelligence things built into it. There are other applications, kind of like in this sort of air traffic controller situation where workload can be very high. UAV drone controllers have to non-stop monitor. There are so many drones, they are doing surveillance, looking for again terrorists or whatever. These kind of a commercial surveillance, the example that I showed you. And eventually it will be both sort of physical and mental, right? Okay. So, the person, I mean, this is a simulated environment, the person is running like a battlefield situation. Now, obviously, we cannot create battlefield, so we create virtual reality or immersive room where you can simulate this running, walking with a virtual reality glasses can show the visual field, while of course EEG is being monitored and cognitive workload and stress are being monitored to see how this person deals with this kind of workload stress situation. As I said, the other one is pilot, co-pilot, cooperative, and you see in this work was done by my colleagues in Italy, and they have this pilot, co-pilot, and what they found that, so this is where it's not true network, they are not truly connected, but correlative, that certain simultaneous things happening at certain times, and sure enough, during takeoff, they are both alertly focusing on similar things. There was a relatively higher level of, as I said, not direct but indirect connectivity. During cruise, nothing much happening, not much. Landing, even more stressful, they are more attentive, interactive, and so on. I think there is a video there. It's in Italian. So yeah, they had pilots put on and see how they can cooperate with each other during this kind of 5 incidents. So this is becoming a rather important field because the world is aging. The male female ratio is pretty symmetric and all that, but look at the aging that's happening. The bulk is shifting to so many very few old people way back, I don't know when it was, in developed countries, so on. So population projection towards aging. So this cognitive enhancement due to this aging factor will be a problem in future. So that's another area where this cognitive engineering may be very applicable. Prevention, does it work? Go and solve mental math problem, crossword things, play music. A lot of these are suggestions, but do they really work? And so these cognitive tools that I showed may be a way to objectively test these things. Otherwise, these are all fun suggestions. Do this, do that, lots of ideas. So there is an interesting graph that says a lot of things go through what are called hype cycles. 3D bioprinting, human augmentation, and then it goes up 3D printing further, and then after a while, there's a really big hype. This is a very old graph, so this is old era where internet, TV and all that hyped up. Machine to machine communication, now that kind of hype isn't working out, not as much as they thought, and then there is a sort of period of disillusionment. So BCI for a while was a big hype, and everybody in China, India is doing BCI. Then people like me said, okay, it's slow, it has this problem, VG is a bit of headache, it's slow, what are, some ALS patients, how many people can you use it? So there's a bit of disillusionment. And then a little better algorithms come, the EEG became dry electrode. Maybe people using this kind of dry electrode, NeoSky or those kind of system, maybe you can apply in some situation. Let's try it again. And then of course everything gets better and better, and kind of like speech recognition. Apple phone, whatnot, Siri versus now Alexa has gotten even better. Okay, all right, it's acceptance. So my point is, all of you hear these Elon Musk kind of video that I showed you during the hype curve, and there's typically often these kind of cycle on hot topics and all that. Tragedy is most of you are going to catch it somewhere here, because by the time the news comes and trickles down to you, the world has probably moved on. So you have to be really alert in picking up the news. There is a sort of delayed gap between cutting edge research and areas and countries till others follow. So now after all these, a lot of people will say, let's do BCI or something, and so you have to be very careful about that. This is my colleague Tassos as acknowledgement, and the postdocs and MRI guy, and this is a grad student and a collaborator and so on. Lots of acknowledgement, but I want. Okay, I think we are really short of time, so I think I will do one last thing, and that is, oh my God, lecture 25. That is what I uploaded. I have not uploaded the lectorium. That I can do tomorrow. But this will also to make you think. So the where we are going is that can humans and machine coexist, right? After all, what Elon Musk, right? You remember what he was talking about? We'll have to be cyborg, because he thinks the AI is going to be so powerful, the humans will have to somehow keep up. So humans will have to, on their own, we are not going to get smarter. Our genetics, our IQ is what it is. And it's been millions of years. We can educate and learn, but it doesn't like our IQs are going up. Our bodies have gotten a bit bigger. So it isn't unreasonable to think that for us to be, the software, the AI, all that is getting better. It's like getting better at astonishing pace. So we're screwed, right? As human being, we are evolving at biological scale. Taking, yes?
At Google, apparently they made AI design another AI, network design its own network.
Yeah.
It's better than anything else which any human has ever created.
Yeah, there are a lot of these news stories. If you guys interact, I gave you some homework, list of Nobel Prize, this or that. You should send it to me or to the person Debasis, so we can share with each other. Yeah.
My project name is AutoML.
Auto.
AutoML.
AUTOML.
Machine.
Yeah. Okay. Obviously, I can't keep up. I wish I'll try to remember, but I'll probably forget. My mind is swimming. I'm right now like seriously between mental fatigue to voice fatigue to how can I make a really tough quiz. I'm looking forward to that for alertness, So because it's like that rain. It's kind of gotten a little monotonous, and this being nice guy giving chocolates and all that, no fun. So between how am I going to go look for AutoML? So if you that website, I'll get to it. But let's create a sharing of that because we want to educate. Many times when you came to questions, so why don't you ask question, because it can use it for everyone. Okay, so what's going on is that this era, like just human Elon Musk kind of thing, he mentioned that human intelligent machine coexistence maybe the future. We just will have to create a intelligent coexistence, right? So there have been, you know, we can go at all levels. I showed you this Star Wars, right? This is a human machine coexistence, right? There's a Luke Skywalker's arm and a machine. They are coexisting, right? It's not like, you know, that machinists take over his arm and has become cyborg or something. So there is examples. So the economist this month said that thought how brains and machine can be made to work together is really like really hot, really interesting for people to think about it. You know, here like this person as an amputee is working so smoothly, seamlessly between himself and the machine, wonderfully, properly coexisting. They are interacting. He's able to control the prosthetic arm and work on it rather seamlessly. You see, so I think it's a good kind of cognitive prosthesis, although that's a bit of hyperbole because we don't have an EEG based control, but as you said, one of you is trying to do EEG, EMG combined, and that would be truly a cognitive prosthesis if you can do that. So this is a good, you know, remember just to review you examples, the human, the brain, the nerve, the prosthetic arms are coexisting. So I think we have come to accept this kind of coexistence in prosthetics, rehabilitation, some level of exoskeleton. We're still a little bit spooked by mental brain cognition and brain interfaces. But there is a coexistence. The nerve damaged person could well be, you know, eventually coexisting with an arm that would provide exoskeleton support or electrical stimulation. So I gave you the examples of brains and robots, like controlling. Can you control a robotic? That should be reasonable. I showed you about Nissan's brain to vehicle interface. You know, if you remember the video, you know.
Dimension to the interaction between vehicles and human beings.
So
To the interaction between vehicles and human beings.
So you know, this is happening now, right? It's like this was announced within the last few weeks. So this is very cutting edge. I mean, it's a bit awkward. I don't know how you're going to wear caps and do all that, but it has presumably overcome the issues of some of the cap and electrodes and eye blink and artifact, and it's somehow augmenting. Actually, did I play this entirely or only partially? I played it entirely, right? I mean, there was left-right decision and some of the other things, but it's of course still a bit of marketing kind of story. It's very important that when you have to look rather intelligent and have a funky art style and dressed with a little weirdly to become, you know, don't become like a very nice suit and tie wearing. You know, flight simulator, I showed you that cognitive flying, or actually in this case in the next generation, we had this person, it's pretty wireless system. So this is a wireless EEG while he is driving, and he can follow and do the wireless tracking. So you know, we can follow the mental cognitive workload during driving. So it is, you know, whether it is used for fatigue or whether for monitoring performance or augmentation. These are a bit of you know, again exploratory work. This is again out of NASA. So this person is sitting in the screen, and it's as if like his screen is that of a space station or something, which has a camera looking down on Earth, and he's scanning the Earth. But or you could put it that way, that he's navigating the space station with his mind. Literally what this person is doing is just either going left, right, or top down, just one or two axes, but it looks cool that you can actually navigate space station. So you know, right, I mean, right. So if you guys get a project from ISRO or something, can you build a brain machine interface for controlling our India space station? You guys can do it, right? Yes? Not a problem. It's just left, right, P300, EEG, this and that. All right, but India, I think Indians want going to Mars, right? We did send out a Martian rover, a Martian space thing, so why not? It's not playing. Yeah, so now let's control a Martian rover with the brain and mind. I mean, why not, right? It's EEG, processing, wireless, goes to the rover, goes left and right, and it's probably moving very slowly, so slow BMI probably would work. So we can have a Martian rover BMI. Seemingly like a good way to end the course, right? I mean, we are now in the clouds. Not we are beyond the clouds. We are in this space. Ooh, wow! Like I'm navigating a Martian rover. So I'm hope that you are inspired, suddenly alert and aroused and so on. Anyway, so therefore it does raise all these fears of automation. Does the humans, there's this thing about New York Times, human machine coexistence, will they take the jobs, right? You know, this is a job queue where robots are in queue and you are in somewhere in the middle. This one is convinced with wisdom of machines, Google appoints a robot as CEO. You know, your whatever your Kharagpur alumni, what is his name? He said bye bye, next one. So you know that means we'll have to figure out some cooperative tools so that these things can. And that's coincidentally what Elon Musk was saying. He's saying they create a fuse system, but at least we have to start with this collaborative tool. The U.S. Defense Department therefore create a lot of these things about seamless human-machine partnerships, human state sensing and assessment, human-machine interaction, cognitive modeling, cognitive machine, human-machine and learning, data fusion and understanding. You see, a lot of this is very important, hot stuff. I mean, you can read neural whatever interfaces and shared something and whatnot. So big defense people are thinking about it, right? So this is further human state sensing, human machine interacts, task and cognition, machine learning, whatnot, fusion. So you know there are these the systems have to be dynamic, adaptive, self-organizing, robust, blah blah blah. Teaming up, right? We'll need to kind of what Elon Musk was saying. We'll have to team up with robots. So robots do the sensing, and we do maybe the understanding, and robots do the automated learning, and maybe we provide a perception. No, this person is a good person. Don't just do face analysis and shoot it. Decision making. Robots will make decisions. Should we override? Kind of interesting. So humans will have to be in the loop, right? Robots, this and that. So that's a pretty picture. Human intelligent machine for future in space program. So augmented intelligence, I said, maybe do you stimulate? Do you do this kind of surprise and virtual, things that we did in those project. So this is some of these is a group of students and postdoc in our institute there who are doing this kind of cognitive engineering work. Plus we have quite a bit of international collaboration in different places in people who want to collaborate. Some of them visit us, some of them we visit, like that Italian group I showed you, so that get ahead through collaborations. You can't just say well, I'm here and I don't have EEG and I can't do anything. There are probably ways to collaborate, whether with a physician. Sorry? I'm kind of like one level in the cloud. I was in that Martian rover time at that time. Okay, so how can man and machine work together? Will robots replace humans? How will neuromorphic brain replace human brain? All right, how many think that way? So neuromorphic brain will be so much better, smarter than replace the human brain. I don't know. I'm very surprised by your negativity. Will robots replace humans? Well, okay. Take your task: cleaning house, doing your homework, taking your test in your place. Lots of it. So robots will replace human. That you agree, but you don't want to agree they'll replace your brain, as if like you are some. What is your IQ? Come on, guys, you're gone. You're dead meat. Human brain project. So that's why I've told you many times that human brain project is built the whole so biologically detailed that at some point it will capture so many things that a little bit in neuromorphic we say, it has many projects like informatics, computing and so on. Lots of money, US also, lots of tools being developed. There's a cognitome type of project, network, fMRI, EEG, connectivity and so on. So there you go. So cognitive engineering is a wonderfully good way to end this whole course. Okay. Good. So you guys have come a long way. Are you ready for the quiz? Yes. Well, but I mean, if, and tomorrow, so how the schedule is. Right now, we are going to walk around.